The second assignment was a quiz on D2L, so it was auto-marked, and I'm just going to go over the results of one particular instance with particular values that D2L generated for me. So the first question that was asked was, what's the most important dimensionless group? And the obvious answer to that is the Reynolds number. Reynolds number gives us the relationship, the ratio between the magnitude of the inertial forces and the viscous forces, and it's always important to know what the Reynolds number is. Maybe not to know the exact value of it if it's really large, but it's important to know how strong the viscous versus the inertial forces are. Second question was a similarity question. It talked about having small particles in air, say a particle 120 microns, 0.12 millimeters in size, traveling at about 11 centimeters per second. Now, small particles like that are hard to examine, so what about a dynamically similar performance for a much bigger particle, 9.5 centimeters, so big, in glycerin? Could we get a similar Reynolds number so that we got the same flow behavior on this larger particle? And if we did, what would the velocity be in the glycerin? So we need to have the Reynolds number for the original prototype. That's the small particle in air. It's going to be the velocity that we're interested in times the length scale, which in this case is going to be the diameter, divided by the kinematic viscosity. That is 11 centimeters per second, so that's 0.11 meters per second, times the diameter in meters, that's 0.12 millimeters, or 0.00012 meters, so we're getting all of this into consistent units, divided by the kinematic viscosity in air, which is about 1.5 times 10 to the minus 5 meters squared per second. So all in consistent units, and we wind up with a Reynolds number of 0.11 times 0.00012 divided by 0.00015 is about 0.8. So I calculated 0.88. Now if we want the Reynolds number of the prototype to match up with the Reynolds number of the model, so for the Reynolds number of the model to be 0.88, then what we'll have is 0.88 equal to velocity times diameter divided by kinematic viscosity. And where this was all for the prototype, the diameter of the prototype, the velocity of the prototype, the kinematic viscosity of the fluid in the prototype situation, the air, this will all be for our model. We don't know what the velocity is, but we do know these other things, so that the model velocity will be equal to the kinematic viscosity for the model times 0.88 divided by the velocity for the model. Or looking up glycerin at about 20 degrees C and being sure to get the right answer out of the table instead of the wrong one, we get about 1.19 times 10 to the minus 3, so much more viscous than the air, times 0.88. Oops, made a mistake there. That shouldn't be a velocity, that should be the diameter of the model. I would have wound up with the velocity down there if I was trying to calculate the diameter, knowing the velocity. The diameter for the model, 9.5 centimeters, 0.095 meters. So let's try that one. 0.00119 times 0.88 divided by 0.095 is 0.011. 0.011 meters per second, or about 1.1 centimeters per second. So a slow-moving flow that we can see the behavior in, and we can probably make some pretty good measurements in. So that was the question that we were asked, was to get Reynolds number similarity. What would the velocity be in the model situation with a much larger particle to get the same dynamic conditions as in the prototype situation with a much smaller particle? Finally, question 3 asked, if we have a diameter of 43 centimeters for a sphere and it's moving in air at 10 meters per second, what is the drag coefficient? So once again, we need to know the Reynolds number, because if we know the Reynolds number for a smooth sphere, then we can we can look up the drag coefficient on a chart or in tables. So if we look at a plot of drag coefficient versus Reynolds number, and it's a logarithmic scale, it typically looks something like this for a smooth sphere. We need to know the Reynolds number. The Reynolds number in this case will be velocity times diameter divided by kinematic viscosity. That's 10 times 0.43 to get it into meters, divided by 1.5 times 10 to the minus 5. Plugging that in, I get 10 times 0.43 divided by 0.123415, and that winds up being 2.87 times 10 to the 5th. If I go in, that's going to be around here somewhere, and up to here, follow across, and I get a number like about 0.55. So I'd say the drag coefficient in this instance is about 0.55. And depending on where you were in the range of numbers that are provided for the auto-marked question, you could wind up anywhere in between about here and about here, which should have given you a number somewhere in that 0.55 ballpark, between about 0.4 and 0.6.